The second tool for Fourier series that we will need is to talk about when does this series an e to the I n theta converge. This will be a fairly simple test. So we want to apply Weierstrass M test. And to do that, we will need that the coefficients are bounded by 1 over n squared. So we will assume, and it's worth noting, we're not saying anything about what this series converges to, we're just saying that it converges to something. So suppose that absolute value of an, and these could be complex numbers, is less than or equal to a constant times 1 over n squared. So there exists some constant. So this is true. Of course, it could be 0, in which case this is not very interesting. Then the sequence of partial sums, and now the indexing is going from minus infinity to infinity, so you have to take it from minus n to capital N. This converges uniformly to a continuous function that we denote as the infinite sum from minus infinity to infinity. Well, let's do the proof of this. This is fairly short. First, we want to decompose this into two normal sums that start from an index. First, we want to decompose the series as starting from a finite index in the beginning. So f of theta would be sum to infinity of an e to the I n theta plus sum from n equals 1 to infinity of a minus n e to the minus I n theta. This way we have two sums to consider. So it's enough to prove that sum n equals 0 to n a n e to the I n theta and the sum n equals 1 to n e to the minus a minus n e to the minus I n theta converge uniformly. And well, how do we prove that these converge uniformly, these series? Well, we apply Weierstrass M test. And this Weierstrass M test, we proved it for real values, but again, it applies just the same for complex values. So what do we have to prove for the Weierstrass M test? We have to estimate from above an e to the I n theta. Well, this is bounded from above by absolute value of an times, well, it's equal, in fact, to the product of these absolute values. Well, this is the absolute value of e to the I n theta, which is cosine plus sine, so cosine squared, sine squared is equal to 1. This is less than just an. Actually, worth remarking that these are just equalities. So this now, by assumption, is less than cn squared, at least when n is bigger than or equal to 1. And how we can use that is that we can set this as mn and apply Weierstrass M test. So Weierstrass M test implies that the first series converges. And similarly, the second series converges. And the final thing we have to observe is that if we have two things which are converging uniformly, so this series and this series, then their sum converges uniform. So if Fn converges uniformly to F and Gn converges uniformly to G, then Fn plus Gn converges uniformly to F plus G. Thus, sum n equals 1 to n, an e to the I n theta from 0 plus the sum from 1 to capital N of e to the a minus n e to the I minus n theta. Both of these converging uniformly converges uniformly to what we denoted as the infinite sum of these things. So after a re-indexing an e to the I n theta. So if we have that the coefficients are decaying fast enough, then we automatically get convergence by Weierstrass M-test. And we get that the limit, therefore, is continuous because the sequences of partial sums are in themselves continuous, as sums of continuous things. As an example, if you have a sum of 1 over e to the I n theta over n cubed, say from n to infinity, this defines a continuous function. And the proof of this is fairly short. an is equal to 1 over n cubed is certainly less than a constant of less than 1 over n squared. And we only need this for n bigger than or equal to 1. Then the claim is obvious. Obvious from theorem. The theorem exactly states, once the coefficients decay fast enough, you get uniform convergence.